Okay, welcome everyone. It's 12:30, so we'll go ahead and get started. This is the Prelim 2 review session for CS 4820. So if you're here for something else and just sitting in the wrong room, you should probably get out unless you want to learn about algo. That's always fun too. Just like arrows. Okay, so just some general announcements. Prelim 2 is on Tuesday, so it's fast approaching. Hopefully the spring break fog is clearing a little bit. The topics are going to be divide and conquer, network flow, and NP-completeness. So hopefully you saw that on Ed or on Canvas, but there will be no questions on approximation algorithms on this exam, even though you guys have been studying it for the last few weeks in lecture. As in the last prelim, you'll have 90 minutes, and it'll be a similar format, so you can expect like a handful of short answer questions and then a couple of longer design questions. And hopefully you can kind of guess what those longer design questions will be based on the things that you've been seeing over the past few weeks. Okay. So just some general tips for the prelim. I wrote a post before the last prelim on Ed. That was like some general tips for just how to follow along. All of that stuff still applies for prelim 2. So if you need a refresher, hopefully after having taken a prelim, if you felt a little pressed for time, you kind of know what that's like and can prepare accordingly. Particularly for this prelim though, you know, the types of questions you're seeing have more of a formula than I think for prelim 1, right? So if you see an NP-completeness proof question, you know that there are a list of things that you have to do. And in fact, you've had 3 problems on it in your homework now, and you've had 3 rubrics basically for these types of questions. You should be able to predict our rubric, right? So like, even if you can't get the reduction, do get as much partial credit as possible, right? So don't forget the steps, right? Like, make sure that you say that your problem is in, that you at least attempt a proof at both directions and an attempt a reduction, right? And if you do all that, you're likely to get at least half, if not, 75% of the points, even if your solution is incorrect, right? On the flip side, if you give us a correct reduction and you miss some of those crucial steps in your proof, then you're not going to be able to get as many points on the problem as you probably should be getting for knowing the correct reduction, right? So just don't forget any of those crucial steps. Read the question carefully, right? The prompts on these questions tend to be a bit longer than the prompts maybe on Prelim 1. And then
induction. So having that base case in your algorithm makes induction go pretty smoothly as well. You can just start off with that base case. And then analyzing the runtime of a divide and conquer algorithm isn't as simple as just the runtime of a regular algorithm, because you have to solve it using a recurrence relation. And a recurrence relation basically talks about your runtime at any specific level of your divide and conquer algorithm when you are splitting it into subproblems. And then solving that is going to get you to that big O runtime that we eventually want at the very end. So a classic example of a divide and conquer algorithm would be merge sort. Hopefully you guys all took 2110, you know how merge sort works. You're dividing it, recursively sorting those subproblems, and then you're merging them together at your last step. And we're going to go over merge sort a little bit later, and you can see how we solve recurrence relations on a more familiar algorithm, but hopefully you know what merge sort is. And then again, proof of induction or proof of correction is going to be by induction. Again, if your algorithm is correct, it should follow pretty naturally. And we're going to do a couple examples of that as well later on. Okay, so integer multiplication. I think you guys saw this in lecture. Yes? Yes, you did see this in lecture. Okay, so integer multiplication is a great example of divide and conquer. So originally, when we do integer multiplication, it's going to be O of n squared time, and so we can cut that down actually to be O of n to the 1.59 time, which doesn't seem significant, but it definitely is. And the way we can do that is we can take out that middle chunk by changing that middle part of that equation. So you see up here, we can represent x and y by x1 is going to be the left half of the integer, and then x0 is going to be the right half. And we can multiply that by 2 to the n over 2 power and get the same exact number. And so what we do then is we're going to be multiplying those two representations of x and y together. And so when we're computing that, originally when you expand out that equation, you're going to have this one section in the middle which we can actually change into different subproblems for a divide and conquer problem. I'm not going to go into it because you guys should have gone over this in lecture. This is just kind of one example of how we can change a runtime from O of n squared to O of n.1, O of n to the 1.5 by reducing the number of subproblems that we have originally. So if we originally have 4 subproblems, after we do this, we'll have 3 subproblems. And that change of subproblems is what makes the runtime for the overall equation go down. So that's just some intuition as to why divide and conquer is so important and how it can make our algorithms a little faster. Okay, again, not going to go over this super in depth. You guys talked about this in lectures 11 and 12, but this is just the overall, this is kind of just what fast Fourier transform does. Just knowing this information is important. You won't have to prove it again because we've already proved it in lecture and in the textbook. But yeah, let's move on from that. Okay, so this is going to be our first example for divide and conquer. Hopefully this can be a little bit interactive because you guys are taking the prelim, so we want oh, okay, no, I'm just going to go over this. The answer's already on there. Okay, so closest pair of points. I'm not sure if you guys saw this already, but the way that we do closest pair of points for divide and conquer, the way I like to solve divide and conquer problems is just like arbitrarily trying to see if I put them into different subproblems, if I can make some sort of clever merge step, and then that's kind of just how I go about it. So when I was doing the closest pair of points, like intuitively, what I decided to do is I'm going to split your section into 2, or I'm going to split my entire area into 2 sections. I'm going to find the closest pair of points in one section, the closest pair of points in another section. Whichever of those distances is smaller, right, I'm going to use that. And then you continue doing that. And then what's the problem that might come up here? The problem that might come up is like when you're splitting into 2 sections, the closest pair of points might actually be on opposite sides of those 2 sections, right? So we have to have some sort of clever merge step or combine step for the conquer part of this divide and conquer algorithm. And so what we came up with is once you recursively find that smallest section, either on the right or the left side, what you then need to do is you need to, it's kind of hard without drawing it, but you need to take the middle section that you split in half, but you only need to make it as big as that smallest section that you have found in those subproblems, because if it's bigger than that, then it won't be the smallest distance of points. Does that make sense? I can also draw that out. But yeah, so that's how you solve a divide and conquer problem like that. In this case, you're not actually like combining anything like in merge sort. You're not combining the results of your subproblems. You're finding a solution inside your subproblem, and at the very end, you're using that solution to make sure that that's the absolute correct solution for your entire problem. Does that make sense to everybody? How we solve that using divide and conquer? Okay, please feel free to ask any questions as well. I know I might be going a little bit fast, but if you have questions, this is your time to ask questions. Yep.
You know that there's not a lot of points.
There's not, sorry?
You know that not all the points were the inside.
How do all, oh, like all the points be inside the middle section?
They're all like, what is like, let's suppose like all the points.
That would like change your definition of the middle section, right? Like you're comparing all the points pairwise to each other. And so if they were all in that middle section, that doesn't make sense because your definition of that middle section is like the one that's like closest, right?
It is closest, but what if there's many?
Yeah, so if there's many, then it wouldn't really matter because the algorithm is just asking you to find the closest distance, right? Closest pair of points. So we haven't specified how to break ties in this instance. If that was part of the spec, then we probably tell you like, oh, just pick an arbitrary point, pair of points if they have the same equidistance. But I think also what you're asking, if all the points were in that middle section to begin with, when we divided, we'd only be looking inside that middle section. Like that would change the space of our problem to just be that middle section, and we divide and conquer on that instead. Does that make sense?
Also, there's a bound on the number of points that can be in that section.
I guess I'm asking, how does that bounding exist? Because let's say divide into like equal corners. Say that if I guarantee there's only how's that?
Because like when you go on the left side, you find like, let's say like the closest pair of points on the left side, is like distance like delta, right? Then like if you make your margin like delta wide, right, you can guarantee that there are at most like 12 points like within those margins, because if they're more than that, then like there would be like, I guess like points closer than delta together, right? But which is contradictory to your assumption.
But you don't have to assume like they're integers or anything, and this would be true.
Yeah, you don't have to assume the integers. Like any distance, like if the closest pair of points on the left side is like, I guess like delta apart, then like if you had more than like 12 points or some constant number of points, right, then like they would have to squeeze together such that like now two pairs of points are close to delta.
Yeah, like we said though, you're not going to be asked to like reprove or regurgitate algorithms and results from the book or from class. So like yeah, I guarantee that no question on the exam will ask you in super granular detail how close to pair points works.
During the exam, we want to use like FFT when we're designing an algorithm. Do we have to like write the steps of FFT, or do we just say like use FFT?
Yeah, in the same way that you would for an NP-completeness reduction, just say like assume that we haven't or like use the independent set problem or whatever. Like yeah, it's the same thing. Just use FFT.
Well, it's like the sorted of x and y coordinates, right? We are assuming that if we have like the x coordinate, we can find the corresponding y coordinate.
Yeah, so you're given just points. You're not giving like a sorted list of anything. You're just given like a set of points, and then you have to find the 2 points with the closest distance to each other. Hello. Hello. I think my microphone. Is my microphone dead?
Is it?
Okay.
Hello. Okay, this is our first exercise that we're going to try doing together. Sorry. Okay. Yeah, so we're going to consider this I'm just going to hold it. We're going to consider this following algorithm. We basically want us to sort this array A in place. I'm going to just let you guys read over it, but basically we have 2 base cases, n is 1 and n is 2. Those are pretty trivial. Sorting an array of size 1 and 2 is pretty trivial. Otherwise, what we're going to do is we're going to set m to be 4/5 n. We're going to sort from 0 to m recursively using this. Then we're going to sort from n minus m to n, and then we're going to sort from 0 to m. All of these are recursive sets, so these are all subproblems. Then we're going to end and then return a. So our question for you guys, you can kind of talk amongst yourselves, is actually it's the next slide, I think. Yeah. Okay. So either kind of think about how you might want to prove correctness for this. So like I said, using induction for divide and conquer problems, either prove correctness of this or provide a counterexample where this algorithm would not sort A correctly. So we'll give you like 5 minutes to do this one, and then we can go over it together.
Like if you're fine. That's the smallest. But they don't ever merge it. So it's just
So like, does that work? Oh yeah.
I have a question. Can you assume like if like n was equal to 3, can you assume that it's
Hello. Okay. Okay. Let's go ahead and go over this this problem now. Okay. So, who thought that this algorithm is correct? Okay. Does who thought it was incorrect? Okay. Does someone want to give me? For if you did think it was correct, do you want to go over? Do you want to go over why, or like what a proof of induction using induction might look like for this algorithm? That's correct. That this algorithm is correct. So yep.
Okay, so there's for any given list, there's pieces. If n equals 1, then the original list just is correct as it is. If n equals 2, then it's right because it places the min before the maximum. Otherwise, it divides into 4/5 and 1/5. Can we look at the original slide? I need to see that, please. Thank you. So the way for it to miss is if somehow the elements in the upper 1/5 are placed in the lower 4/5 after line 14. But we know that that won't happen because after line 13, like after sorting 0 to m the first time, all of the upper 1/5 elements in total have to be in the upper 1/4 of a of 0 through m. And so line 14 has to catch that. And so the upper 1/5 elements have to be placed in the correct position. And then by line 15, all the rest of the elements are also placed in the correct position.
Yeah, that's exactly right. So let's go over. So yeah, if you guys didn't hear him, we can go over it right now. But that's exactly how you go about proving this kind of divide and conquer algorithm problem. Yeah, so basically the claim that we want to prove is what he was talking about. We want to prove that the largest n minus m elements of A are going to be contained in the subarray from m to a or m to n. Sorry. And then once we prove that claim, proving that the entire list is going to be sorted follows pretty naturally, and we'll go over that afterwards. So the way this proof is going to work generally, I won't read it all out because you guys can go over these slides again if you're confused later. But if we have this entry, say A at index J is going to be equal to gamma. It's one of the largest n minus m elements. We want to prove that it's going to be in that subarray m to n. And how we're going to prove that is if j is greater than or equal to m, then clearly it's going to be inside that subarray. If it's not, then we can use that inductive hypothesis. We can claim that from everything up to that point, it's going to work correctly. And like what he said, line 13 is going to ensure that that element gamma is going to be inside that subarray from, what is it, m to n. And yeah, so this is kind of how it goes. So it must be that j prime is going to be greater than or equal to m minus 1, because we're looking from if j is less than or equal to m minus 1. And then if we figure that all out, we get to 2m minus n. Yeah, so sorry, that was a really quick overview of how the algorithm works. But then after you're able to prove that the n minus m largest elements are going to be in that subarray m to n, then we can say that it follows that the smallest m elements of A are going to be in those indices from 0 to m minus 1. After applying induction on all those cases, then we can say that this is going to work for all instances or all lengths of n for A. Yeah, and then it implies that the output A is going to be sorted in increasing order. So yeah, this algorithm would work correctly, and that's kind of how we would prove by correctness a divide and conquer problem. Does that make sense to everybody, how we went about proving that? Yep.
Is the proof of termination not included in the proof of correctness?
Yeah.
Proof of termination. Does this algorithm should terminate when A is equal to 3, like it says?
So it's the floor. We set m to be equal to the floor of 4/5 n. So we'll terminate.
Oh.
Yeah. Sorry, the notation is kind of small there.
This algorithm is actually a variant of algorithm sort, and it's I think it works for any m that's greater than a half. So if you want to Google it, it's kind of interesting.
Okay. Cool. All right, we're not going to do all these exercises. Okay, we can do this one. All right, so we're going to go. What? Yeah. The runtime? Oh, we'll go over that in a second. Yeah. So local minimum finding. So we're given an array of distinct integers, and we want to find an index such that its position is, or the value stored in that position is smaller than the values in the surrounding cells. So we want to make sure that at an index I, it's going to be less than I plus the value at I plus 1 and greater than the value at I minus 1. Okay, any ideas for divide and conquer algorithm for this problem? Yep.
Have to just keep following the direction where you're decreasing.
Yep. That's the answer. So we're going to split it into subproblems of 2. We're going to split into 2 subproblems, try to find the minimum in those subproblems, and then if we can't find one, we're going to follow, like he said, we're going to follow in the array of the decreasing value. So do you want to go to the next slide, which we go over the? Yeah. Okay. So our base cases, right, that's important. We should have mentioned our base cases before we moved on to the subproblems, because that's going to be your free points for divide and conquer algorithms. So your base cases are going to be if n is less than or equal to 2, going to be pretty easy to figure out if that works. Another constraint on this algorithm is that it has to be within bounds. So like if the index is n minus 1, it can't be a minimum, right? Because there's no other value at the array index n. Okay, so if not, then we're going to split it. We're going to let m equal the floor of n divided by 2. We can check if the value at that index is a local minimum. If it is, great, recurrent it. If it's not, we're going to recurse. So if the value in the index before m is going to be less than the value at m, then we'll recurse on that problem. And then if not, we're going to recurse on the other half. So like he said, we're following the direction where the value is decreased because, yeah, okay. So that's kind of just like a general overview of how we would solve that problem using divide and conquer. Does that make sense to people, or like how we would come up with that on an exam? Does anyone have questions about this? How we solved this problem?
It's a really simple version of like just following like smaller numbers until you hit something that must be.
Okay, just ignore that. You guys don't need to know what gradient descent is. Okay, so right, so now we're going to talk about the runtime. So this is a pretty simple algorithm. So you guys know how runtime relations work. We know we split into two subproblems of size n over 2. So we have, and then we have a runtime of constant time for each subproblem, right? Because checking if a value is greater than or less than the indices around it is going to be constant time. And then you saw in class that this is just O log n, and we're going to talk about how we're going to unroll that and how we can find that using Master's theorem, and then also just geometric sums in a second. Yep.
How is checking if AM is a local minimum?
So this is the runtime for the merge step. So whenever we're merging like subproblems in this case, there's no extra work that we have to do. All we have to do is check whether or not the surrounding indices are greater than or less than. That's constant time, and then checking which one is smaller in order to recurse on that subproblem, which is also constant time. So like in merge sort, that would be O of n instead of O of 1, because when you merge it, that's linear time in order to merge those two subproblems together. Good question.
All you're doing is checking.
Cool. Okay. Let's skip this one. Okay, solving recurrences. So you're dividing your original problem into k subproblems, and then you need to combine the runtimes of all those subproblems in order to get the answer to your original problem. So obviously you can't just do what we normally do with runtimes, which is kind of just like go through it line by line and say like, oh, there's a loop that's O of n, because that's not going to work and account for all the runtimes of these k subproblems. So we need to consider both the runtimes for splitting and then also combining those k subproblems. So the general, can we go to the next slide? Yeah, so the general form is going to be this. So we have t, which is going to be less than or equal to that. So Q is going to be the number of subproblems we split it into. So for merge sort, we split it into two subproblems. So Q would be 2. P is going to be the reciprocal of the size of each problem. So for merge sort, we're splitting it into 2 halves. So that's going to be n over 2, because the subproblems are going to be of size n over 2. And then the combined step is the runtime for combining them. So right, merge sort, it's going to take linear time to combine those two subarrays together. So that's going to be O of n. This is not the final runtime because this is like T of n, right? It's not in big O notation, which is what we want. And to solve that, we can use a couple of different tactics. The first one's going to be the Master's theorem. Or nope. Well, I already went over that. It's okay. Yeah, so this is just basically a formal explanation of what I just said, right? Two subproblems, so it's 2t. Each subproblem is half of the size of the original problem, so it's n over 2. And then the runtime for the merge step, or like the merge, the runtime at each like subproblem step is going to be O of n. Okay, so now we're going to go over. Yes, so one tactic that you can use is the Master's theorem. The only thing is that this only works for recurrences with a linear time combined step, so you're kind of limited in this aspect. So so this is just something, if you want to memorize this, you can. You can also, there's also going to be a more general method we're going to talk about in a second. But yeah, so if there's a linear time merge step, so if this part is O of n, then you can use this. So if Q is less than P, it's going to be O of n runtime. If Q is equal to P, it's going to be O of n log n, and then if Q is greater than P, it's going to be O of n to the log PQ. Yeah, that's going to be your runtimes. I'm not a huge fan of the Master's theorem because one, you are constrained to the linear time merge step, but also it can be kind of tough to memorize those three as well. So what I like to do usually for recurrence relations is using geometric sums. Okay, yeah, and I've kind of shown you like my thought process when I solve these kinds of problems, because I find it can be kind of tough to just look at like a bunch of numbers on screen. Okay, so we start out with a runtime. So I start out with the runtime. T of n is less than or equal to 3t, 2 over 3n, and then c of n squared. So when you see the c of n squared, all that really means it's like O of n squared. I'm just multiplying it by a constant c, just because that's easier for me to visualize. It's not super necessary, honestly. But the way that I approach this, when I think this was like when I was taking the class. So you start off with a problem of like size n, right? And then we know that we're splitting it into 3 different subproblems because we have a 3 in front of the t. So we split into 3 subproblems of size 2 over 3n, right? And then we continue doing that all the way down to our base case, which I've assumed is 1 for this problem specifically. So we have to continue splitting all these subproblems until size 1, right? Because once you get to size 1, you know, you can just execute the base case and you're going to get an actual answer. And then we also know how many levels there are in this like weird triangle thing, right? Because we know the size that we're splitting the problem down, so we're cutting it down exponentially by 2/3. And so we're going to get to log 3 over 2n as like the number of levels that we have overall. And that's going to be important a little bit later. And then the next step is going to be finding out the runtime at each level. So at the first level, it's just going to be c of n squared. The second level, we're cutting it down into smaller subproblems. So it's going to be c times 2 over 3n squared. And you're going to add that up 3 times, and that's going to account for the runtime for that level. And you're going to continue doing that down. Usually only takes like 2 or 3 levels to start to uncover some sort of pattern. And that's really important because you want to be able to generalize the runtime for each level based on what level you are at. So for example, for the second level, we get that awful number. And then for the third level, you get that number. And then eventually we can generalize this to this is going to be the runtime at level I. Does everyone understand how we got there and like the intuition behind what we're doing right now? Yes? Okay. Yeah, so then once we get the runtime at each level, then it's going to get a little bit easier because we know how many levels there are, the runtime at each level, and so we can construct a sum. So in this case, we have log 3 over 2n levels, so we're going to sum from 0 to log 3 over 2n, and at each level, this is going to be the runtime. So eventually you solve for that, you get you take out like everything that's not really related to the problem or to the level. And then this is great because this is like in geometric sum form, which hopefully you guys know about geometric sums. So once you get down to this form, we can go to the next slide. The next one after that. Yeah. So once you get down to the geometric sum form, then we have these rules for geometric sums, which hopefully we all know about. So if r is equal to 1, it's just going to be O of k. If r is less than 1, it's going to be constant time. And if r is greater than 1, it's going to be O of r to the k power. Okay, so this can also be kind of annoying to memorize as well. I find that if I'm prioritizing things to memorize, I'd rather memorize this than the master theorem because you know this is going to work for every recurrence relation. Then you can finish solving it, right? So we have the sum that we were able to find by unrolling our runtime. And then in this case, r is going to be 4/3 and k is going to be this. And so we can solve it using that. So where k is equal to the number of levels. Does that make sense to everybody? For solving recurrences, that's going to be a big part of if you have a divide and conquer problem. So being able to solve the recurrence, I don't know what the test looks like. I can almost guarantee that there's probably going to be something related to solving recurrences. So does anybody have any questions about how we went over that? Yep.
And again, like how r equals 1 is O of k, and like those 3 things, like where does that come from?
Like a derivation of that fact.
No. I can't right now. Like, I don't think I have the time or actually the knowledge to do that. I would just suggest memorizing it.
Where would it like? Where would you apply it? Like.
Oh, sorry. Okay. Can you go back one slide? So we get a sum of this form where this is r. 4/3 is r because that's just like how a geometric sum works. So yeah, that's on the slide right there. Cool. Any other questions about recurrence relations?
So you can leave the runtime in the form like O of r to the k. You don't need to further simplify, right? So like if r is 4/3 and k is log 3 times n, then a valid runtime for the problem is 4/3 to the log 3 times n. And you can literally write O of r to the k where r equals something and k equals something.
Yeah, you don't have to simplify it. That'd be awful. Okay. You can, yeah. Okay, do we want to go over how we would find the recurrence relations for 4/5 sort? Yeah? Okay, does anybody want to try their best at what a runtime or a recurrence relation might look like for this algorithm? Yep.
3t then 4/5
plus O1.
Yep. And so how did he get there? We were splitting into 3 subproblems. Each subproblem is size 4/5n, and then the merge step is going to be constant time. Yep. And then I'm not going to go over solving that because we just did. Oh wow. Okay. No. Yeah, it's okay. Okay. Cool. So that's divide and conquer. Anyone have any overall? Yep.
Why do we need to write like the recursive relation? It seems like if you just make the tree like enough to come up with the summation and then the runtime. Like, so why do we need to come up with the recursive?
Your tree comes from
Yeah. So yeah, the tree is just a direct visualization of what the recurrence relation is stating. So you still do need to write your recurrence relation out because the tree doesn't necessarily tell you much. I mean, I guess you could find the runtime, but you still need the recurrence relation in order to write the tree in the first place so that you can know like the runtime at each step and then the size of the subproblems and the number of subproblems. Yep. Yeah. For this problem, so you would be unrolling it like similarly to how we did it before. So, there's no like writing space, but you're splitting into 2 subproblems, each of n/2 size, and it's constant time at each level. So your runtime is going to be like based. It's just going to be like based on how many subproblems there are at each level, like the size of the subproblem at each level. It doesn't really depend on n, which is why there's no n in this runtime, right? Because like before it depended on n squared, but since it's constant, it doesn't. All it depends on is like the number of subproblems at each level, which is going to be 2 to the I. So like at level 1, there's going to be 2 subproblems. At level 2, there's going to be 4 subproblems. And since it's constant time, it doesn't depend on n. It just is talking about like the number of subproblems at level I. Does that make sense? And then we're summing it over log 2n levels because that's how many levels there are when we recursively cut it down into 2 every time. Yep.
Isn't dividing conquer a bit much horizontal?
Yes. Yeah.
But you can do it in logging times. Oh, this is like a bad algorithm.
Well, this is a shitty algorithm that was like given in a different context. Yeah, that's why I like the algorithm itself.
If you have to find the minimum of an arrays, could you also do that?
Not the minimum. Well, because like the idea of minimum is that like you keep going like I guess left or right based on like whether or not the element left or right of the current element you're looking at is smaller, right? And eventually it gets to the point where like you're either at a little bit or you actually get it.
Oh, okay. Sorry. Okay.
Okay. Any other questions for divide and conquer? Yep.
When I write down my recurrence relation on the test, like T of 1 is less than C, like the base case.
I doubt it. I don't know what the rubric's going to look like, but I don't think that's super relevant.
And it is true, as in like your recurrence relation should theoretically have a base case, but we don't get that.
If you remember to put it, you might as well put it.
That's true. If you remember to put it, you should probably like. I mean, you're not going to lose points.
Yeah. Your base cases are important so you can figure out how many levels there are going to be. So like when your subproblems are going to get to your base case. Yep.
Why is T of n less than or
Because I think it's because like that's just like the max, like that's just like the upper bound of the runtime for that level. Awesome. Okay, let's go on to network flow. Okay, so you guys should know the basics of a flow network by now. So you have a flow network, which is a graph of vertices and edges, and each edge has a capacity of C sub E assigned to each edge, E and E. Okay, so basically what flow is it's going to be a function that maps each of these capacities to an integer value, where flow is the upper bound of that integer value, and has 2 constraints on it. So the first one is capacity, which is basically saying that your flow needs to be less than or equal to the capacity, but also greater than or equal to 0. So you can't have negative flow. And then conservation, which is essentially saying all the flow out of S, the source S, needs to be the flow into E, or into T. Or wait, sorry, that's kind of like the overall constraint. But the regular conservation constraint is just saying like the flow of the edges going into vertex B needs to be the flow of the edges going out of vertex B. Yeah, sorry. The value of the flow is going to be the sum of the edges out of S, which is going to be equal to the sum of the edges into T if you conserve flow throughout the entire network. Okay. Okay. So residual graphs and augmenting paths. So given a valid flow F, we're going to form a residual graph G of F. And what that's going to look like is you're basically going to have backwards and forwards edges. So, yeah. So for an edge E with a capacity CE, the residual graph is going to contain a forward edge for the amount of flow that we can still push, which is basically capacity minus flow, and then a backwards edge for the flow that's already for the flow that we can push back. That's kind of a more intuitive way of thinking about it instead of just looking at like the numbers up here. So forwards edge is going to be the amount of flow that we can push forward, and a backwards edge is the flow that we are already pushing forward, so we can push back if necessary. Yeah, the edges for which capacitor 0 can be ignored. Obviously, we can't have any negative flow. And then an augmenting path is going to be a path on the residual graph from S to T using those forward and backwards edges. Yep. Okay. Yeah. So if every edge on an augmenting path has a capacity of at least, I actually don't know what that delta. Okay. We're able to augment F to get a new flow where we add that delta onto our original flow. So we need to be able to find that S to T path. We need to find a delta such that that's the every edge has a capacity of at least that, and then we can add that to our original flow. And that's how we eventually find max flows. Once we can't find an augmenting path anymore, then we know that we have the value of our max flow. Everybody understand residual graphs? Awesome. Okay. Yeah, so Ford-Fulkerson algorithm also should be very familiar. It's going to be basically exactly what we just went over. You're making residual graphs. You're finding an augmenting path. You're going to update the flow if you can find an ST path. Once you can't find an ST path, you're done. Return the flow. And the runtime is MC, which is the number of edges and the value of the flow, times the value of the flow.
So one thing I'll say about runtime real quick is I've gotten a lot of questions of the forum like, oh, is this technically pseudo-polynomial because the capacities can be bounded? It is true that in general, Ford-Fulkerson is pseudo-polynomial. You can construct problems for which it's strictly polynomial. So let's say we're reducing to like bipartite matching. The runtime of Ford-Fulkerson in that setting will be strictly polynomial because you have unit capacities on every single edge. However, we don't really, like if we say give an efficient algorithm for max flow, we don't care if it's pseudo-polynomial. Right? Like Ford-Fulkerson is good enough. There do exist strictly polynomial algorithms to find max flows. Two of them are Edmond-Karp and Pusher-Label, but you're not expected for knowing the details of those algorithms. So Ford-Fulkerson will always be good enough for finding max flow. So do not be too concerned with the fact that it's
Okay, who wants to help me find the residual graph for this one? Okay, let's start with this one. Forwards edge, backwards edge, capacities.
5 and 5.
Okay, yep. So it's gonna have a forwards edge of 5 because that's the amount of flow we can push. Backwards edge of 5. I'm just gonna go through the rest of it. That was okay. So we're pushing 5 flow on this edge. We can push 5 backwards. Yeah, it's gonna look like that. So hopefully you guys should be able to figure that one out on your own as well. Okay, let's move on to cuts.
So I mean, if you have an edge with infinite capacity, right? Like, what's the forward and backward edge look like?
Forward is infinite, backward is
Also, whatever the flow is. Exactly.
Yep, you can always push more flow if your capacity is infinite. So the value of the flow, if we go back, do you want to go back to that residual graph? So we can find S to T paths, right? So we can go here, and then here, and then here, and then here, and then here, and that can be an ST path, and then our delta for that is going to be 2. So then we go to the next slide, and that's going to be our overall flow. So once we add that delta 2 to all the paths that we just took, we're going to get this. So our value of flow is going to be 12, right? Like 7, 5, and 7, and 5. Awesome. Okay, let's move on to cuts. Okay, max flow min cut theorem. This is a super important one for network flow. So for every flow network, you're going to have a minimum capacity of an S to T cut, and that's going to be equal to your max flow. So knowing that can be really powerful. Knowing that the value of your flow is always going to be equal to the minimum capacity of an S to T cut. That's gonna be super important. That's kind of like your bottleneck. When we talk about a bottleneck, that's what it basically is that once we have an S to T cut, the minimum of those capacities is going to be as much flow as you can push through, right? Because otherwise, like we wouldn't be able to get to T if we're pushing more flow than that. So that can be kind of considered like our bottleneck in a flow network. And then we also have flow integrality, which is just saying that like if all capacities in a flow network are integers, then we can find some sort of maximum flow that's also an integer. Or yeah, okay. Okay, does anyone want to try to find the minimum cut for this one? Should be pretty straightforward. Yep. There's like 3 minimum cuts here. So we can cut here, we can cut here, we can cut here. It's just going to be 12 regardless, which we already know because we just went over this problem. Okay. Yep. So, yep. Okay.
Does everyone remember like the standard algorithm to find a min cut?
You basically find the saturated edges. Once you found the max flow, you look at you basically do BFS and then see where you can't go anymore, whether it's just graph edges become 0 and you can't move any further, and all of those nodes kind of behind that impossible layer of zeros. That's going to be your A in the mincut.
Yeah, it's basically everything's still connected to the source after you run Wilkerson and you find that residual graph. Right?
Yeah. Do we need to know about how you have on the homework we proved a bunch of things, like if you have a min cut, then there's no path from A to B, and so on. So it seems like really useful for like I think project selection is really useful. Do we need to know those theorems? That's not so important.
I mean, those are useful things to know. Yes, so you don't need to reprove results. We're not going to give you a homework problem on the exam, but you can feel free to use any results you proved in the homework on the exam.
For this problem, is that supposed to be a max flow?
Yep.
You repeat how to get the cut.
The min cut. Yeah. So do you want to repeat like how you can get the min cut?
Yeah, sure. You find the residual graph, then you just do a you do a BFS from your source node, and if it's connected, to the source node somehow, then it's part of your A, and then everything else is part of your B. And make sure you don't include your 0 edges in your residual graph.
Yep. So it's BFS on a residual graph. So finding how you can get from source to sink. I would say that I think it might be. I would recommend to actually like state how you're going to find it if you are using max flow min cut in your algorithm. Even just saying like, oh, I'm using a BFS to do this instead of just saying like, I'm going to find a max or I'm going to find a cut like somewhere. That might be helpful just because I don't know. I just don't know how trivial that is. So I would like caution you to state like I'm using a BFS or kind of go through like what you're doing there. Okay, so let's move on to reductions. Okay, so we use max flow in order to reduce from other problems. So there's a lot of cool reductions that we've done in our homeworks. So max flow reductions are going to be, these are some examples, and then these are some examples of min cut reductions. So it's going to be the same regardless, like you're making a flow network, but whether or not you're using max flow or min cut in order to prove that is going to be like the difference here. So if we go on to the next slide, yeah. So designing the reduction, I've had a lot of people come into my office hours and ask like if there's like some method that they can go through. There's not like a method for how to go through these kinds of reductions. You kind of just have to, you know, like try to figure it out. Usually it's going to have, I mean, there's obviously going to be a source and a sink. Usually there's going to be like 2 layers of nodes. It's going to look kind of like a bipartite matching. And then you're going to draw those edges based on the relationships between those nodes. So you saw that like using the funds for the donors and whatever, like there's a relationship between donors and charities. And then there's also a relationship between charities and the max amount of funds that they're allowed to get from each donor, right? So those would be the edges. Yeah, so again, there's no like cookbook rule for designing those kinds of gadgets. But if there are more advanced constraints, you might need more advanced gadgets in your network flow. Okay. Yeah. So proving correctness of reduction. So there are two different types of proofs of correctness. I think this is pretty important because sometimes I saw on the homework a lot, like a lot of people were able to prove one direction and then not the other direction. So for feasibility problems, which is basically just asking like, is this possible? So like for the donors, like, is it possible to create some sort of assignment such that every charity gets the amount of money that they need? I think that was like what the problem was. That's a feasibility problem, asking if it's possible for some sort of, assignment of funds or whatever, a flow. So feasibility problems, you need to prove that if there's a solution to the original problem, then there's a solution to the network flow problem and vice versa. So there's an if and only if relationship between the original problem and then the network flow reduction problem. So in this case, you'd be talking about finding a flow value that's greater than or equal to V. Or capacity that's less than or equal to C. So this is like if you were using max flow, and then this is if you were using min cut for capacity. And then for optimization problems, it's a similar reasoning, except that you need to show quality. So like the quality of your solution is going to translate. So if you find the most optimal solution in the original problem, your network flow is also going to find the most optimal solution. The important part for reductions for network flow is that you're proving both directions. I saw a lot of times it's like pretty simple. One direction is usually pretty straightforward. Proving the other direction can be kind of tough, but just making sure that you are proving that there's an if and only if relationship to both, like backwards reduction proofs or anything like that. Does that make sense, everybody? Network flow reductions. We're going to go through an example in a second. Okay, cool.
All right, so generally when we're doing reductions in network flow, often but not always it is the case that if it's a feasibility reduction, it's usually max flow, and if it's an optimality if it's an optimality reduction, it's usually min cut. There's not a good reason for this though, because it's really trivial to change problems from feasibility to optimality, and in fact, many of our NP-complete problems that we see are optimality problems that are just reworded as decision problems, right? So don't like always use that framework, right? You have to think a little bit more carefully about whether it's better to represent your problem as a cut or as a flow. This one is hopefully pretty simple and along the lines of things that you've already seen before. So problem is we have a company that wants to treat its employees to donuts, and a box of donuts from FF's Effing Fluffy Donuts contains one donut of each of the 12 flavors. So each box is a dozen and they all have their own different flavors. So the company collects a list from their employees, and it's basically the flavors that each employee would like of donut. And they want to determine, whether ordering the boxes of donuts is enough to make sure that every employee gets a donut that they would like, right? So can you design an algorithm, polynomial time, or if it becomes pseudo polynomial for Fulkerson, that'll be fine as well. That takes as input, the flavor lists for every employee and the integer b, and decides whether or not that ordering b boxes is sufficient enough to get what they would like. So I'll give you I don't know, we're doing pretty good on time, so I'll give you at least 5 minutes to think about this, and then we'll go over it.
Yes. So back to the just want to find that's why we said you just want to find a point where the left and right are smaller or greater than. So what about the boundaries? Yes, the boundaries are boundaries count, right? The boundaries are okay. That's, the idea is they're just converging to it. Right. So if you do the boundary and the thing on the right is greater than it, then you found the thing that's behind it. Define it. Yeah. So obviously, there isn't always a look. They're all because we just had a constant. Assume that they're okay. Connect and if it's truly constant throughout, then you can just say the constant doesn't.
Generally, you're not going to get a problem that's
Fox has like any of
You guys have a reduction? Go over it.
No, you would see.
All right, so hopefully you guys had some time to think about this. We're gonna go over it now. Do you want to hit the next slide, Andy? Okay, so the idea here is that we can encode this decision problem as a max flow problem, right? So we're gonna reduce to max flow. So let's consider this following flow network. We're just going to make a source node and we're going to make a sync node, obviously, because it's a flow network. And the source node S is connected to a node for every employee, right? So we have some subset of nodes E1 to En, and all of these have unit capacity. And the reason it has unit capacity, actually, can someone explain to me why it might have unit capacity? Yeah?
Each worker only gets one donut.
Right, each worker gets a single donut. So we only need one from the source to every employee. So then there's another layer of nodes, and we're going to use these as kind of like our flavor nodes, right? So we'll have F1 through F12, and each edge basically between the employees and the flavors is going to be like the preference lists of the employee, right? So the employee wants some subset of the 12 donuts. We're just going to draw a node going from each employee to each of the 12 donuts, also with capacity 1. Right. Now, each of these flavor nodes, we have basically B of these donuts, right? However many boxes are ordered, we have that many of each individual flavor. So we're going to draw a node from each flavor node to the, or an edge from each flavor node to the sink with capacity B, because that's how many of those donuts that we have to offer to all the employees. Okay, so then you can just run Ford Fulkerson on this network, right? And if all of the edges leaving the source are saturated, right, then we know that every single employee was able to get their donut, right, one donut. Otherwise, the answer is no. So does this make sense? Yeah?
Can you switch the order and make it like the source node to the employee nodes and then the
I think you can, yeah. So yeah, you could switch the order of the layers and I think it would still work. Yeah?
Are you allowed to have people like not waste donuts?
Oh yeah, donuts can go to waste. Yeah, that's fine. Yeah. Oh, question?
From the flavor nodes, the sync nodes, infinity.
Infinity.
Yeah, analyze like the result, the maximum apparent, like what it should be.
Yeah, that also works. Yeah.
You can't make it infinity, right? Because then everybody like 16 donuts if they have one thing.
So like B is a constant, right? So we could just check, right? Oh, okay, never mind, maybe not. Okay, so here's a little diagram that I drew up of this reduction. So just a tip for the prelim, pictures are truly worth 1,000 words when it comes to reductions, right? Like this not only makes it easier for you to explain what you're doing, but it makes it infinitely easier for me to grade. And in fact, if I see a correct picture, right, and I get that you get the gist, I will probably ignore your proof and just give you most of the points or full points, right? So, okay, that's kind of a joke, right? I still have to read your proof. I still have to read it, but, right? But the picture, all right, settle down. So the picture, right? We have our source and our sink, and then we have our capacities as described, and then you can just draw, you know, I use like a dot, dot, dot for like layers, right? Because obviously you're not going to draw like 12 actual nodes in a row. Or if you do, props to you for having the time to do that on an exam. Now, a second reduction that you could do is you could expand the flavor nodes to just be a donut node, right? And so you could have, for every flavor node, you'd write B of those nodes, right? And then you would draw edges from the employees to each of those donut nodes. That blows up the number of nodes in your graph quite a bit though. And so you have to be careful, right? Like if it is the case where B is trivially larger than, where B is greater than the most requested flavor, right? Then the answer is just automatically yes, right? But otherwise, you can run this reduction to see if it still works. If you don't make that check at the beginning, then you risk your reduction possibly being pseudo-polynomial time and not actually polynomial time, right? And the reason why is because you're making way more nodes than you originally had, and so your max flow is going to blow up a lot too. That's just something to keep in mind. Like this is a better reduction because it's less nodes. But if you have B times 12 of these nodes, then B times 12 could be greater than n, in which case you would have a pseudo-polynomial reduction, not a polynomial.
But isn't it okay to have a pseudo-polynomial reduction if anyway falls?
So if we say like efficient, then yeah, pseudo-polynomial is fine, right? But the question here specifically said polynomial time reduction. So yeah, yeah.
If you were to make like B types of each flavor,
Yeah.
would it be like a bipartite matching?
Kind of, yeah. Because you would just have every employee connected to every flavor node that they like, and they would connect to every single donut of that node. Yeah. So also, yeah. Let me go back and correct something that I said earlier, right? Like Ford-Fulkerson will always be enough to solve the problem on the exam, but if we say polynomial, we do mean polynomial, which means you do need to think about the runtime of your reduction, and if it is pseudo-polynomial, then figure out how to make it polynomial, right? Like this is a polynomial time reduction. The one where I described if you make a single node for every single donut is not a polynomial time reduction unless you do the check at the beginning, which checks for the most requested donut and checks the value of b against it, right? If you just always construct that network with 12b or 12b donuts, then it does not become polynomial anymore. Does this make sense? Yeah. Because if 12b is like greater, or if 12b is much bigger than the number of employees, right, then your reduction is dependent on b, right, which is a number, which is like pseudo-polynomial, right? But if b is like sufficiently small, then it still becomes polynomial with respect to n. Yeah. And it's just like you have all the subsets d, right? Whichever one is the highest number out of all of those. Or like whichever one shows up most frequently in all of the sets. Yeah. Yeah.
Like you have to check every single person's thing, right?
I mean, it's a polynomial the number of people there.
Yeah.
Which is an input. So.
It's O of n times 12, right? Yeah. Yeah.
Why adding like the
Like a node for every single donut would not be polynomial,
Yeah.
right? So if okay, so if b is greater than the most requested donut, basically, right, or the number of the most requested donut, then we trivially have enough boxes to satisfy everyone's desire, so we're done, right? If it's not the case, we can then construct the network with all the donuts, right? If we don't do that check, right, then what we have is a really like large number of nodes that are dependent on b, right? And b is a large number now, right? Like b is a possibly big number where we trivially could have just looked and satisfied everyone's desire, but now we can't, right? And so our reduction is now dependent on the size of b, which is an integer, right? That makes our reduction pseudo-polynomial because we're making a number of nodes proportional to b, right? In this case, we're only ever making 12 nodes and then making the capacities b.
Like the size of b is log n, right? So if you make like b nodes, then you're making like order log n like exponential in the size of b.
But can't we consider b as an input to the algorithm? So
No, b is an input to the algorithm, but its size is log.
It's exponential in b though. It's not polynomial or in log b. Yeah. Yeah. Right? Because b is like we discussed this in length when we were talking about like the knapsack problem, right? Like b is given as an integer, which is written in like some number of bits, right? And it takes exponential in that number of bits to actually write down a node for every single one of those, for every b, right? Okay. So the takeaway is, if you can find a simpler reduction like this, please do, right? This is a good reduction, right? Okay, so the runtime, I think this is pretty simple. Yeah, we'll skip it. Okay. So this is a min cut reduction. I'll just give that away at the start. Maybe I should have made you guys think about that a little bit more, but yeah.
Sorry, just going back to the donut one.
The runtime or the flow reduction?
Proof of correctness. Like, did you?
Oh, I did not give a proof of correctness on this. This problem did not actually ask for a proof of correctness, so I didn't get one. Yeah. Okay. So we have a Congress that's made up of N members, and they're trying to form a committee of experienced members, right? And so you want committee members to have at least 2 years of experience in aggregate. There's an issue though, in that we have like ideological differences between members of our Congress. And so each member is unwilling to sit on the committee with another member with which they share ideological differences, right? So, in general, if we tried to solve this problem, it would be NP-complete. But we're going to throw another aspect of this problem in, which says that members of Congress either belong to the right party or the left party, R or L. And members that belong to the same party do not have ideological differences, right? So this actually becomes enough to make this problem tractable. Next. Okay, so for each member of Congress, I, given by some integer 1 through n, you're given TI, which is the number of years that member has been in Congress, right? You're also given a subset of people that the member shares ideological differences with, and you're guaranteed that if they're in the same party, they do not share ideological differences with that other member, right? So what we want is a polynomial time algorithm that decides, does there exist a committee with a total number of years that's greater than or equal to t, in which every member is willing to sit with every other member on the committee? Okay. Right, so this one's pretty tricky. This is, I'll give you guys 5 minutes to think about it. I don't think most of you will get it in 5 minutes, but if someone does, that'll be great. Yeah.
think cut reduction is sort of like the same. Like you see you went for most of them, but then you have to get the cut. Whereas like a max reduction, you just pick it up. You might not have any but somebody else can. Assume that like the same party has yeah. It's a positivity that you love. Wait, so you don't like someone who get party. You don't like the entire party. No. He says like everyone's just in a party. I know. So you just like one person. No. Good wow. Same party. Yeah. So if you're both in the party, so you're both in the art party, so that's does that mean the L party? I don't like the art party. Yes. So it's like oh no. Where are you coming from? Because they don't have anything.
All right, so for sake of time, I'll cut you guys off there. We need enough time to go through NP-completeness, so good. 2 slides forward. Okay, so we'll solve this with a min-cut reduction. And so here's the idea. We need to make a graph G, right? So we're going to basically make this bipartite. We'll have a source and a sink, and then a layer of nodes for everyone in L, and a layer of nodes for everyone in R. And from S to every node in L, we'll draw an edge with capacity Ti, which is the years of experience of that party member. And from 2T from every node in R, we'll also draw a node Ti, which is the years of experience for everyone in that party, right? And in total, between L and R, we should have N nodes. Does that make sense? And then, so for I and J, right? Basically, if, oh, that should be L, not B, my bad. So if I is in L and J is in R, and I has an ideological difference with J, then we're gonna draw an edge from I to J with capacity infinity, right? Why would we do this? Why are we drawing an edge with capacity infinity from members with ideological differences? Yeah. Right. They must always be on the same side of the cut, right? If we have a forward edge with capacity infinity, then we can always reach basically the next node in the residual graph, right? So they will always be on the same side of the cut. Okay, so we're gonna let A star, B star be the minimum cut in G, and the committee that this corresponds to is going to be L intersect with A star, and then R intersect with B star, right? And what we're claiming is, so yeah, the nodes that are on the S side of the min cut and the nodes that are on the T side of in R on the min cut, right? And we claim that this corresponds to like an optimal committee in the sense that it maximizes the total years of experience with members of no ideological differences. Okay, so we'll return yes if and only if this committee has at least T years of experience in total. So in other words, the capacity of that minimum cut needs to be less than total years of experience of everyone minus the target, right? So yeah, this goes back to what I said earlier. I was like, often if we have an optimality reduction, we'll use min cut, but this is a decision problem and we're still using min cut. And indeed, this is also an optimality reduction that we're maximizing the years of experience of our feasible committee, right? So you should be able to recognize kind of when to apply a max flow versus when to apply a min cut, right? And the idea here is that like, if we take certain committee members, we cannot take other committee members, and that's really hard to encode in a max flow problem, so we're gonna encode it as a min cut problem instead.
This seems a bit like seems quite hard for a test problem.
This is hard for a test problem. This is hard for a test problem. I was struggling to find a decent min cut problem, so yeah, like I couldn't do like I tried to do application for it, I could not figure it out. So. You have a question?
Yeah, question number one: why is A intersect of A star and D or B star?
So we'll go ahead and we'll prove this, and then you'll kind of see from there. Yeah. Infinity. Oh, there's no conflict. There's no edge. No edge. Yeah. Okay. Can you move on to the next slide? So here's just like a picture of this, right? And so, you know, the committee that you form will depend on the cut, right? And we have arbitrary numbers T1 through T4 and T5 through T8. So I can't necessarily just like tell you exactly what the main cut is. It'll depend on these integers, right? But suppose that the nodes outlined in red are in A star and the nodes outlined in B are in B star, or the nodes outlined in blue are in B star, right? If that is the case, then what we said was the committee is going to be L intersect A and R intersect B, right? So the committee that we get is nodes 1, 2, 5, and 8. So it's the nodes in L that are on the left side of the cut and the nodes in R that are on the right side of the cut, right? So hopefully this is a decent visualization. Like if A and B is the min cut, then that is the committee that we would form. Yeah? Right, so the nodes outlined, like blue versus pink? Or the outlined? Yeah, so the outlined, I said if it's outlined in red, it's an A star, and if it's outlined in blue, it's an B star. Right? If A and B is a minimum cut, A star, B star is a minimum cut, right? So remember, if they share an edge, they will most definitely share ideological differences, and they will always be on the same side of the cut, right? So 1 to 6 and 2 to 7 must have ideological differences, right? Because there's an edge with capacity infinity, and in any minimum cut, they will always be on the same side because of that infinite capacity edge. Okay. Next slide. All right, so the runtime of this. Our graph has 2n plus 2 nodes, right? It's just one for each commit. 2n plus 2. Well, maybe L has n and R has n. And M will be bounded by this number of edges of n squared, right? Edmond-Karp's algorithm will find us a minimum cut in m squared n time. You don't need to know Edmond-Karp's, but for this solution, we just use Edmond-Karp. And so that gives us an O of n to the 5th farming time, which is polynomial. And so the proof of correctness, we want to show that there exists a committee with experience greater than or equal to T, if and only if there's a min cut in G with the correct capacity. And I actually think I'm gonna have to skip the proof so we have enough time to do NP-completeness stuff, but the proof is in the slides and it is complete. Sure. Yeah, what's your question?
Why in the last slide we want them to have differences be the same?
The same side of the cut? So if we make it so that the people with ideological differences are on the same side of the cut, that means that like by our formula that we develop to find the optimal committee, which is L intersect A, B, R intersect B, then we'll never select 2 people with ideological differences, right?
We don't intersect between, the union between L and R, once they have differences.
No, because they're wrapped in intersections, right? Like L intersect A star and B intersect R, B star intersect R, right? Like they cannot have ideological differences because we're only taking the members in L who can work with the people, right? Because the reason they're on the same side of the cut is that it represents that there's an ideological difference, right? So if they're in different parties and they're not in the same side of the cut, that means that they don't have an ideological difference. Does that make sense? Okay. Okay. So if we have an ST cut with capacity that's less than or equal to our threshold basically that we set, we're considering that committee C and we're claiming that it has no members with ideological differences and that the total years of experience is at least T, right? So this is kind of like the quality of the solution in addition to the feasibility of the solution, right? And here you can kind of work through a proof by contradiction to solve it. And there's some sums, but it's just kind of rewordings of things.
Pretty much the idea is like the way you select it is, or the value of the cut corresponds to the years of experience you're missing out on. Right? So if you minimize the value of the cut, you're also minimizing the number, like of all the committees, of all the valid committees, like the years of experience you're missing out on by selecting certain people.
Yeah.
And then so when you minimize that, you maximize the total years.
Yeah. Yeah, so the value of the cut represents basically the amount of years of experience you're missing out on, right? And so of all of valid committees we can form, we want to minimize the amount of years of experience we are not selecting, right? And the inverse claim is that given a committee C in which no two members have ideological differences and the number of years is greater than or equal to T, consider the ST cut of the form that we created, right? It must be a minimum cut on our graph. Okay, I will take like one or two last questions about network flows and then we gotta move on, yeah?
You think we have to do correctness? Like on video?
We have to do proof of correctness?
Yeah, because on the when the countries said that we probably won.
Yeah, I don't know. Yeah. Yeah?
Are we allowed to convert the network to a problem where nodes
Have to be what? Oh, no. Yeah. Okay. Yeah, so let's move on to NP-completeness. So this is probably going to be like the bulkiest question on your exam. This is also my favorite unit in the course personally, so I think this stuff is really interesting. Let's just go over some basic definitions and terminology first though. So P is a set of decision problems that we know can be solved in polynomial time. And when we say decision problem, we mean yes/no problem, right? So it's really easy to turn optimality problems into decision problems by just setting a threshold and saying yes or no based on whether or not the quality of the solution meets that threshold. NP is a set of decision problems where there exists a polynomial time verifier. So that means that given a candidate solution to the problem and a problem instance, can I check whether or not the candidate solution satisfies the problem instance, right? And we say if we can do that in polynomial time, then the problem is in NP. NP-completeness kind of characterizes the most difficult problems for us to solve in NP, right? It's kind of an unknown question of whether or not we can solve them, but we know that these problems are hard for us to solve because we haven't figured it out yet. We formally put a notion on this. So if a problem is both in NP and it is NP hard, then it is NP complete, right? And NP hardness is this idea that every single problem in NP can be reduced to the problem we were trying to show is NP hard. Does that make sense? Does all that basic terminology, is all that terminology clear? Okay. So we learned in class that P is a subset of NP. Can anyone just review or real quick explain to me why is it the case that P is a subset of NP? Yeah?
Because if you're verifying it, you just solve the problem again.
Right. If we have a solution to the problem, right, solve the problem and then check it against the answer, right? So constructing a verifier for any problem in P is very easy because we have the thing that solves it, right? Okay. Cool. All right, so this is kind of another application of reductions. And this polynomial time CARP reductions, it's the same thing that we're doing for max flow min cut reductions. It's just applied in a different context, right? So we say that X is at least as hard as Y if it's the case that if we're able to solve X efficiently, we could also solve Y efficiently. In other words, we can use X as a routine to solve Y, then X must be at least as difficult as solving Y, right? So we say Y is polytime CARP reducible to X means that, it's that notation there, the less than or equal to with a P. And this means that X is at least as hard as Y, right? So why do we reduce from like known NP-complete problems to the problem we're trying to show is NP-complete? Why do we not reduce the other way around?
Because you already know that it's at least it's hard.
Right. Like there's no point in making a problem harder to solve, right? Like just because I can solve something with SAT doesn't show that the original problem I had was hard to solve, right? we're saying, you know, it doesn't really put a bound for us to say that SAT is at least as hard as some polynomial time problem. And indeed, any problem in P can be trivially reduced to anything in NP-complete. That doesn't mean that the problem in P is hard. Yeah?
So what is this definition of like hardness? Is it like the time complexity of the solution, or like just like how hard it is to solve?
Right. So what we call hard is like everything in the complexity class can be reduced to it, right? I mean that if we had a solution to solve this problem that we claim is hard, we could solve everything else in the complexity class, NP. Yeah, that's all this notion means, right? It's not necessarily a runtime thing. Now, in the case of NP-completeness, right, we're looking at P and NP-complete, right? So NP-complete problems, we currently do not have polynomial time algorithms to solve, right? So for us, that means that it's hard in that sense, right? But you can put the label hard and the label complete on any complexity class, and there are many complexity classes above P and NP that have the same labels. Yeah. Okay. Another question I got asked. So the distinction between NP-completeness and NP-hardness, right? So like, why do we bother distinguishing between these terms? Every problem that we see in discourse that's NP-hard will also be NP-complete, right? So the reason we distinguish is because if we want to be like correct in what we're saying, there are problems that are NP-hard that are not NP-complete, in the sense that there are problems that can be reduced to everything else in NP, but do not have polynomial time verifiers, so we cannot place them in NP. Right? So that's why we distinguish between those two words. Okay, so one example of reductions is like bipartite matching can be reduced to max flow, right? And then in fact, we use that all the time in our max flow reductions. Is we reduce a problem to max flow, and we say that max flow is at least as difficult to solve as a problem we're trying to solve. Okay. So the contrapositive of the reduction also holds. If we can't solve y in polynomial time, then we can't solve x in polynomial time, and that perhaps is more useful for us in terms of like when we show a problem is NP-complete, that means that if we currently can't solve the x in polynomial time, we also can't solve y in polynomial time. So yeah, the direction of the reduction was a common tripping point, and hopefully after doing enough of these homework problems, you recognize which way you need to go. And we never reduce the other way around, right? It doesn't make sense for us to reduce a problem to an NP-complete problem. We need to reduce from an NP-complete problem. Also, so the polynomial time carp reduction operator is transitive, right? So that's why it suffices to show that once we have a single NP-complete problem, we reduce from that NP-complete problem to the problem we're trying to show is hard. We don't need to reduce every problem in NP to the problem we're trying to show is hard, right? Okay. Well, any questions up to this point? Good. So the NP-completeness proofs, right? It's a pretty safe assumption to, you know, guess that there will probably be an NP-completeness proof on your exam. So suppose that we want to show the problem foo is NP-complete, right? The first thing that we need to show is that foo is in NP. So please don't forget this step. You'll lose like 3 points immediately, or 2 points. I don't know what the exact point value is. But if you don't show this, you'll lose points, right? So please show that your problem is in NP by just constructing a verifier and then verifying that it is indeed polynomial time. You don't always need like the tightest runtime. You know, if it's clearly like, you can say linear, you can say quadratic, and it doesn't need to be like super, super tight. But please don't say the wrong runtime, because that will lose you points. Right, then you want to design a reduction from some NP-complete problem X to the problem foo. So pick some NP-complete problem and basically assume that you have some oracle or some black box algorithm that solves foo and use that to solve the NP-complete problem. Then you need to calculate the runtime of your reduction, and you need to explicitly state that it's polynomial time. This is probably where people lose points the most because they just forget this step. So make sure that you say that your reduction is polynomial time. If it's exponential, if you're making an exponential number of calls to this oracle, or if you have a reduction that takes exponential time to construct, then it's not a polynomial time reduction and doesn't show anything about the difficulty of your solution. Yeah?
Can we just say polynomial, or do we have to say linear or quadratic, or?
It should be evident to us that you know what you're talking about, right? So like, don't just say clearly it's an NP because we can construct a polynomial time verifier. Please explain to me what the verifier is and some notion that you understand that it's polynomial, right? We're not gonna be like super nitpicky on this, but if you just say like, oh, it's obviously polynomial, that's not enough, right? Like, and the safest way to always guarantee that you're correct is just to give the runtime, right? And hopefully your verifier isn't that complicated, so you should just be able to tell us what the runtime is. Yes?
You have to prove the verifier to correctness.
Prove the correctness.
Usually the verifier will be true.
Yeah. And it should be pretty obvious, right? So yeah.
There are some like cursed verifiers, but we won't ask you questions about.
Yes.
We have to like describe a certificate.
Yeah. Right. So I mean, your verifier takes in some input, right, which is a problem instance in the certificate. So you should tell us what that input is and how your algorithm iterates over it or whatever it does. Next. Yeah, your certificate also needs to be like polynomial in the size of your input, right? So like, please don't construct exponentially sized certificates. Again, that should not be a problem for most of the problems that we're considering in this course. So then you want to translate the arbitrary solution to x to the solution to foo, right? So this is a proof of correctness part. It's if there is a yes instance of x, then there must be a yes instance of foo. And then finally, the backwards direction. If there's a yes instance of foo, there must be a yes instance of x. And this is probably harder. And so you want to be careful here that, you know, there aren't types of solutions that you haven't considered, right? So basically, this is like the counterexample. In fact, yeah, my proof the other day was actually broken by another TA. It was the Hamiltonian cycle one on flow saturation. Yeah, I came up with that proof like a year ago, and then someone found a counterexample during our grading session. So if you did that reduction, I'm sorry, but but you have to be really careful to think of these counterexamples on your exam, because if you kind of just like make this part too trivial, you're going to miss an example that probably invalidates your reduction. Yeah.
Say how to represent the binary string.
As binary, no. So the question was, do we have to say how to represent like our certificates or our problems as binary strings? No, that is more of a computability theory idea, and we're not going to get into that for another like month or so. Yeah, the reason why a lot of our solutions kind of have that baked in is because, you know, more formal notions of NP-completeness rely on those definitions of more precisely capturing what it means to be, you know, polynomial time solvable using Turing machines. But at this point in the course, we're not there, so don't worry about it. Okay. So, you know, how do you recognize like which problem I should be reducing from, right? This is probably the most important step of an NP-completeness proof, because if you mess this up, you're gonna have a lot harder time, right? Technically, every problem is reducible to every problem. So, you know, you could pick anything, but some might be much more difficult, or even like, you know, impossible for us TAs to even recognize like that is possible to reduce from. So you want to pick the right problem, right? So packing problems are something of the form where you have like an at least in there. Independent set tends to be a good option. Covering problems, if you have at most and you want to cover a set, you know, set cover, vertex cover. Sequencing problems where we have to take like a sequence of decisions, Hamiltonian path or Hamiltonian cycle, et cetera, et cetera. And if all else fails, 3-sat is a good starting point. And this is basically the exact same thing that I just said. Question? So Hamiltonian path is like, I must take like a very specific ordering of edges, right, to get from one place back to my starting point. It's like, if there's a dependent sequence, if there's an ordering in which I must take something, then Hamiltonian cycle is a good starting point. Yeah. Okay, so here's our first practice problem, and I think I made pretty good time on that part of the review. So are there any questions on just general NP-completeness stuff before we go into the practice problems? Okay, cool. So here we have a problem called double sat. So we have a Boolean formula phi. The notation is a little weird. Basically, it's a function of those literals, right, or variables. It's not necessarily like it's x1 comma all the way up to xn. And it's called doubly satisfiable if there are two distinct truth assignments to its variables, x1 through xn, for which phi is true, right? So it takes in a Boolean formula in conjunctive normal form and outputs whether or not it's doubly satisfiable. So for example, we have this input here, which consists of this CNF. And the answer is yes, because we have two truth assignments that make this CNF satisfiable, right? So yeah, we want to prove that this problem is NP-complete. And so we want to prove that there's some other problem that we can reduce to this problem. So I'll give you a couple minutes to think about it, and we'll kind of regroup and go over it.
Is there any restraint on like the size of this CNF?
It's just like this. It's n clauses and n literals and n clauses. The same way, yeah, you can specify like the size of the CNF and variables. That's
the size of each clause.
It's just like it's the same as stat. So. The next one will be fun. I mean, there were like four.
You did Hamiltonian cycle. It's the rest of the proof.
Well, that doesn't have to. It doesn't have to be that forward. It just has to be. Well, yeah, like that. I know. I know what I mean. It doesn't have to be like 2, right? Doubly satisfiable if there's doubly satisfiable if there's at least like produce three sets by like for every clause like negating clause like
That would always make her think trivially, like the forward direction becomes really trivial, like reverse direction. You have 2 satisfying assignments. It doesn't apply that universe. I'll try that.
okay. Actually, wait, you can't just flip it. Then if you guys,
Okay, so let's go ahead and go through the solution for this problem. First of all, what's the first thing we need to prove when we're trying to prove that double sat is NP complete? That it's in NP, right? So can someone just kind of, briefly give me a verifier that proves that this is in NP? Yeah?
If given like 2 assignments, you assign it for all the variables.
Yeah.
And then you just check the first time whether it's satisfied, and the second time where it's satisfied, and it'll be like full.
Right. Yeah. Just given 2 assignments, just plug them in and check if they both work. Right. So go ahead and next slide. Yeah. So a certificate is going to consist of 2 truth assignments, x and y, and the certificate has length O of n, which is number of variables, which is polynomial in the input length. So remember that your certificate does need to be polynomial in the input length. The verifier is just going to check if x and y are distinct, right? So this is a lot of detail for a verifier, but this would technically be the most correct version. So do account for things like this, right? Like if x and y are the same verifier or the same assignment, then you aren't really doing your thing. So if x and y are both distinct, then it's going to check that they're both satisfying assignments, and you'll just iterate over the clauses and then all the literals. Apparently this is mn time. Oh, I see. Okay, yeah. So there's almost going to be mn things that you need to plug in. So cool. We have a polytime verifier. Yes.
When you're checking against each clause, we can't just bound
number of literals in each slot.
Yeah. So I mean that's why it's MN, right?
Okay, sure.
Yeah. Like for 3-sat, like yeah, you could say oh it's 3 in every clause, right? But I mean in this case you can't. So
I mean, if you have duplicate variables, then like they don't matter. Because like they have the same value. Like
So should we just assume that it's O of 1 to check against each clause with an arbitrary number of literals?
no, it'd be the
like because there's at most like I guess 2 n literals in every clause, right? So it's and there's m clauses. Is it? Yeah, and there's m clauses. So there's technically at most 2 m n things to plug in.
Okay, I'll ask about this later.
okay. So next part. Okay. Oh, actually, go back. All right. Did anyone come up with a reduction? So I heard one that you just added 2 new variables. Yeah.
Oh, that's the same thing. Is that x?
Yeah.
One is x, not an x plus
Yeah. All right. Good. So you can go to there. Okay. So the reduction is really, really dumb. Right? I don't really like this one, but yeah, that's true. So let y be some variable that's not in our original CNF. You can just add a new clause to the end. That's just a tautology. So you just and it with y or not y, right? And we claim that if phi is satisfiable, then this phi prime is doubly satisfiable, right? And that's because we can assign y to like either true or false, and that last clause will be satisfied. And so regardless, like if our first thing was satisfiable, then we have 2 truth assignments, right? One where y is true, one where y is false. And if our first thing was not satisfiable, then it doesn't matter that y is always true. The first thing is not satisfiable, so our CNF is not satisfiable. Okay. All right. So how many people cracked this? I'm curious. Yeah. All right. So a good number of people. Oh, it was like 4 or 5. Yeah. So this falls into the category of reductions where I think is like really just a rephrasing of the original problem with some extra kind of small gadget that you need to construct. So just being able to recognize problems like this is kind of useful for NP-completeness problems.
And just to add on to that, like especially on exams, like the kind of NP-completeness reductions you'll be asked to do, like aren't like the ones you see on homework, like come up with like gadgets or whatever. Like it'll be stuff like this. Like it's like restatements of problems you've seen, and like you just have to like come up with something more clever.
Yeah. Yeah. So yeah, like I think the 3 NP-completeness problems you guys have seen thus far are pretty tough. You should not expect to have something of that difficulty on the exam. In fact, one of them, Ishan just gave you a construction and said, just prove it. And even that was pretty hard, right? So you will not have something like max cut on your exam. You will not have something like flow saturation on your exam. But, you know, that doesn't mean that your reductions will be trivial on your exam, right? So you should practice as much as you can. I think the book is a good source of practice problems. These slides, the next 2 problems actually really like. Speaking of, let's get into the next problem. Okay, so this problem is called the Steiner tree problem, and it's actually one of CARP's like original 21 NP-complete problems, so it's kind of a cool problem to know about. It also comes up a lot in circuit design, so if you're interested in that stuff. So we're given a graph G equals VE and a subset R, which is a subset of V, and these nodes are required or terminal nodes, and a number K and N. And so the problem is to determine whether exists a subtree of G that connects all of the nodes in R using no more than K edges total, right? So a subtree has to be connected. It has to include all of the nodes in R, and it can optionally include nodes that are in V minus R. And the nodes in V minus R we call Steiner nodes. So in this example here, the white nodes are our terminal nodes or our required nodes, and the black nodes are our Steiner nodes. And we can create a Steiner tree with K equals 5 edges, right? We just take the cross, which has K equals 5 edges, and connects all of the nodes in R. Does that make sense? Okay. So before you guys go about proving NP-completeness of this problem, there are a couple versions of this problem that are tractable in polynomial time, right? So for example, what if K equals N? What problem does this reduce to that you've already seen? No. It's a spanning tree, right? It's a minimum spanning tree. If we're allowed every single, right, we just need to connect every single vertex, right? Okay. Oh, actually, sorry, I phrased that horribly wrong. No. What if all of the nodes are required, right? If all the nodes are required, then it's just a spanning tree problem, right? And if only 2 of the nodes are required, then it's just a shortest path problem between 2 nodes, right? So there are versions of this that are tractable in which we can figure out the yes or no answer in polynomial time. But yeah, in general though, for an arbitrary subset of nodes, this is not tractable. So prove that's NP-complete. This one's kind of tough. So I'll give you a hint. I think you should start with vertex cover and think through pictures and see if you can come up with anything.
required ones, the black nodes on the picture. So it says the white nodes. It should be the black nodes on some of those.
So the black notes are the required ones. Yeah, like required.
Okay, so also for sake of time, we'll go ahead and move on to the reduction. Did anyone figure this out or kind of get somewhere with it? Yeah? So the one issue with that is you assume a vertex cover, right? But you're not allowed to assume that there is a vertex cover.
I mean, you have a vertex of a problem.
Yeah. Oh, you just make every edge and make it turn.
Yeah.
Oh yeah, that's actually, it's very close. Can you flip these slides? Okay. So what we're going to do is we're going to set all the nodes in V, right? And so this is our original V, right? Our graph, our input to vertex cover. We're going to set all of those nodes to be Steiner nodes. So these aren't required, right? Also, yeah, clearly it's an NP. Do not say that on your exam, but I'm just skipping it for brevity. Now, for every edge, we're going to insert a node like into the edge, right? And we're going to make this a required node. And then we're going to create a root node that kind of like roots our tree, right? And this is also going to be a required node, and it's going to connect to all of the nodes in the original graph, but not the nodes that we just added to be required nodes, right? So this root node will connect to every Steiner node. And we claim that our new graph G prime has a Steiner tree with no more than k plus cardinality E edges, if and only if G has a vertex cover with no more than k edges. Right? And obviously this is polynomial time because all we're doing is just inserting nodes and inserting edges, and we can do that polynomial in the size of the vertices and the size of edges. So before we move on to the proof, here's like a visualization of this, right? Because I think just reading all the text makes this kind of hard to understand what we're doing. So let's say that this is our original graph, right? And the graph on the left is G, and the graph on the right is going to be G prime. And so the blue nodes are all the Steiner nodes, right? So these are the nodes that are originally in our graph G, and we're just leaving them and we're making them Steiner nodes. Then for every edge, what we're doing is we're inserting like a pink node, right? And these pink nodes are required, right? So every edge basically just gets a new node inserted in between the two endpoints U and V. So now we have like U to W and W to V, right? And then we're creating this root node that connects to all of the blue original nodes that we had, okay? And so then the Steiner tree that we can form, right? So this has a vertex cover of size 2, right? So we can create a Steiner tree of size 6 by just going from the root node to all of, we're taking basically the intuition here is that we're going to take the edges that connect to the vertex cover, if there is a vertex cover, and then obviously the vertex cover must span all of the edges, right? So we can then, with an additional E edges, connect to all of these required edge nodes that we constructed. This kind of makes sense. Is a picture helpful? Yeah?
Explain again why we're adding E.
Why we're adding, like, why is it K plus E? Right, because, so the K edges we are basically using to connect to like the vertex cover, right, if there is a vertex cover. And the remaining E edges connect to the edge nodes that we created for every edge, right? We made one node for every edge, and all of those are required. So we need E edges to connect to them. Technically, actually you need E minus 1, because you see one of them gets 2 connected to it, right? So you actually only need E minus 1. But for the sake of explanation, I'll say it's E, right? The intuition is that you're just connecting to every edge node that you created from the vertex cover, and you have to be able to do that from your vertex cover because it's a vertex cover, right? I see blank stares. Yeah? Like the whole reduction? Yeah. So remember, we have our original graph G. We keep that original graph G, right? And we make all of the nodes in that graph Steiner nodes, right? They're not required. And then what we're going to do is for every single edge in that graph, we're going to like splice a node into it, right? So if we have UV, we'll create UW and WV, and W will be a required node, right? So for every edge, we have one of these nodes. We also create a root node that kind of is separate from the graph, right? And we connect those to all the Steiner nodes. Right? And the idea is that if we connect it to all the Steiner nodes, if we have a vertex cover, our tree can then just go from the root to the vertex cover, and from the vertex cover to all the edge nodes, because the vertex cover must span all the edges, right? That's the intuition. So the proof is hopefully fairly simple, right? In the forward direction, like if you have a vertex cover, then we can create the Steiner tree with the procedure I just described, right? Take the root node, and then take the edges that go to the vertex cover. Those will be Steiner nodes, right? The nodes in the vertex cover will be Steiner nodes, or not required nodes, right? But then we can use those Steiner nodes to kind of anchor us to all of the edge nodes that we created that are required. In the backward direction, if I have a Steiner tree with K plus E edges in it, right? Then, I must have a vertex cover because there can only be K edges that are actually selected in the Steiner tree from the root to the rest of the graph that I originally had. If I had more than K edges going from the root to the graph that I originally had, then I wouldn't be able to connect to all of the edges, all of the required nodes, right, with only K plus E edges. I would need more edges to connect to all the required nodes. But I said I could do it at only K plus E, right? Yeah?
I just don't see how, like, if we're not connecting the source to the required node, how are they going to end up connecting to each other?
The point is, if there is a Steiner tree, it must connect to the source to all the required, or all of the vertex, not the required nodes, the Steiner nodes, right? They're not going to connect directly to required nodes. The whole point is that the E edges go from the things that the root is connected to the required nodes on the internal part of the graph, right? Because you cannot just reach, you cannot reach one of the edge nodes from the root, like directly. You need at least 2 edges to get there.
What if we just connect the source node to all the required nodes?
Then you would like trivially have a Steiner tree, right? Because like you can always like just take the nodes that are required, right? But like that doesn't necessarily imply a vertex cover on the original graph. Yeah. Okay. So I mean, this is a tough problem, right? I will say this did show up on an exam. I think it is a hard problem for an exam, and so. But on the final, there was a hint given for this problem, and here I've omitted the hint. So, so on that exam, they introduced a new NP-complete problem and then said reduce from that new NP-complete problem. I didn't want to introduce a new problem, so I chose a different reduction. So I think without introducing that hint, this becomes much harder, in which case that this exam, or this maybe a bit harder than what you would see on an exam. But the point is it has shown up on an exam, and it is a reasonable question to like ask you guys to kind of understand. Okay, so we're 5 minutes till time. I have one more NP-complete problem in the slides. Do you guys want to go through it, or would you rather just take open questions on material? Go through the last problem? Okay, so let's go through the last problem really quickly. Next slide. Oh, you want to do this one? Okay. Okay, so go back one slide. Okay, so this is called monotone almost all true stat. And the idea is that a monotone stat formula is a stat formula with no negated variables. So only positive literals can appear, right? And a monotone formula is pretty easy to satisfy. We can just set everything to true, right? And we'll always satisfy this assignment. In this problem, we have a stronger goal than what's normal satisfiability. So we want to make sure that in each monotone stat clause, at most one variable evaluates to false, right? And each clause has at least 2 variables in it. So this is still easy to do if we set all variables to true, but this becomes a little harder if we require the assignment to set some number of variables to false. So next slide. So in the monotone almost all true stat problem, we're given a monotone formula phi. So again, no negations, it must be monotone. And we ask if there's a way for us to set k of these variables to false and the rest to true, such that no more than one variable in each clause is false. Does that make sense? Okay. Oh, I did not provide an example. I said in the formula above. Oh, and that's okay. So in this formula, right, if k equals 1, then we can, I think this works, right? We can set x4 to false, I think. Yeah, and it still works. But if k equals 2, then it doesn't work, right? Okay. So we want to show that this problem is NP-complete, right? So I'm not going to give you guys time to think about it. I'll just talk through it. So next one. Okay. Clearly it's an NP. Yeah. So to see that it's NP hard, we're going to reduce from independent set. So here's an example of a stat reduction that does not just reduce from another variation of stat, right? I think this one is useful to understand as well. So what you can do is you can use a variable, right, xw for every node w in the graph, and you're going to add a clause for every edge in the graph, right? And so your CNF is just going to be the and of all the clauses that you formed, and each clause has exactly 2 literals, right? And it basically represents for every edge in the graph you have xu or xv, right? Okay. So is it polynomial time? Yes, because you just write out 2 m terms, right? Based on the number of m edges in your graph. Okay. So I'm going to give you the exact same graph that I gave for the last problem. Label the nodes A, B, C, and D. Then your CNF is just the and of all the edges, right? So we have like XA, XB, XA, XC, et cetera, et cetera, et cetera. Right? And so we're claiming, if we have an independent set of size 2, right? So say it's like A and D, then we can set XA and XD to false and the rest of the variables to true. And this would give us a monotone almost all true stat instance with k equals 2 variables set to false, right? We can just set A and D to false and our thing still becomes satisfied, right? Okay. So the proof here is not too involved once you understand the construction, right? It's basically, there's a one-to-one correspondence between solutions of independent set and solutions of the satisfiability problem. So given a set of k nodes, S, in V that form an independent set, you set the corresponding variables in the independent set to false, and thus you will always be able to satisfy the constraints, because if more than one term was set to false in the clause, there would have been an edge corresponding to 2 variables in your independent set, right? But the definition of your independent set ensures that no 2 variables in the independent set share an edge, right? Similarly, suppose that I'm able to satisfy the monotone almost all true stat problem, you can just take the variables that are false and they must form an independent set. By the same logic, right? The converse or the reverse direction holds very naturally. This problem makes sense? Kind of? Okay. Cool. So again, we went through these problems really fast, so I would encourage you to go through the slides again afterwards while you're studying for this exam. Good luck, and yeah, ask on Ed if you have any questions.